In France, assembly has begun on the world's biggest nuclear fusion reactor as an experiment to see if fusion can really be a source of limitless, clean energy.
ITER will be the first experiment that shows that we can get a net gain, so more energy from fusion than we deposit in the plasma to heat it.
The world of nuclear energy is one dominated by brilliant minds, where lots of innovation is happening. However, ITER, a monumental project that once promised great breakthroughs in nuclear energy, is close to shutting down. What is bringing this powerful project to its knees, and what does it mean for the future of nuclear energy? Keep watching to find out. What can bring 33 of the most powerful nations together? Not the Soccer World Cup this time, but the ITER project. The International Thermonuclear Experimental Reactor, ITER project, is an ambitious international collaboration aiming to prove the feasibility of fusion as a large-scale and carbon-free source of energy. Fusion, the process by which the sun and other stars produce energy, involves combining light atomic nuclei, like hydrogen, to produce heavier nuclei and tremendous amounts of energy. The primary mission of ITER is to demonstrate that it is scientifically and technologically possible to capture this energy for use on Earth. The genesis of the ITER project can be traced back to the mid-1980s, at the height of the Cold War. In 1985, during a summit in Geneva, then U.S. President Ronald Reagan and Soviet leader Mikhail Gorbachev proposed an international effort to harness fusion. The formal agreement was reached in 1988, when representatives from the European Union, then the European Atomic Energy Community, Japan, the Soviet Union, and the USA, began the initial ITER design phase. Over the years, the project expanded to include 7 members, representing more than half of the world's population. The current members are the European Union, through Euratom, the United States, Russia, Japan, China, South Korea, and India. In 2006, after extensive negotiations and evaluations of multiple potential sites, the ITER members decided to build the facility in Saint-Paul-les-Durance in the south of France. At the heart of ITER is the tokamak, a magnetic confinement device designed to hold superheated plasma at conditions ripe for fusion. The tokamak's name originates from a Russian acronym meaning toroidal chamber with magnetic coils. How does this invention work? There are several aspects to it. Number 1 is magnetic confinement. The tokamak uses powerful magnetic fields to confine and stabilize the hot plasma, preventing it from touching the walls of the containment vessel. Number 2 is heating the plasma. For fusion to occur, the plasma needs to be heated to temperatures exceeding 150 million degrees Celsius, which is about 10 times hotter than the core of the sun. This heating is accomplished through a combination of methods: ohmic heating, or passing a current through the plasma, neutral beam injection, and radio frequency heating. Number 3 is deuterium and tritium. ITER will use a mixture of deuterium and tritium, 2 isotopes of hydrogen, as fuel. When these isotopes fuse, they produce helium and a neutron, along with a lot of energy. Number 4 is diverter. At the bottom of the ITER, tokamak is a component called the diverter. It is designed to handle and remove the waste material from the plasma. Number 5 is superconducting magnets. ITER employs large superconducting magnets to generate the strong magnetic fields necessary for plasma confinement. These magnets are cooled by liquid helium to make them superconducting, which ensures that they can carry the massive currents required without losing energy to electrical resistance. How much has ITER cost its sponsors? As with many international mega-projects, the budget for ITER has grown over time. Initially, in the early phases, the project was estimated to cost around 5 billion euros. However, as of the last update in 2021, the cost of ITER has risen to approximately 20 billion euros. It's worth noting that this figure could continue to evolve as the project progresses. There are several reasons for the cost overruns. Technical challenges. Fusion is an incredibly challenging process to reproduce on Earth. This means the technologies and methodologies needed are groundbreaking and often untested on such a scale, leading to uncertainties and unexpected problems that can inflate costs. Logistics of international collaboration. Coordinating between the 7-member entities, each of which is responsible for delivering specific parts of the reactor, has proven more complex and time-consuming than initially anticipated. Regulatory and safety measures. Building the world's largest tokamak requires stringent safety and quality assurance processes. Ensuring that ITER meets the highest standards has sometimes led to delays and added expenses. Despite the costs, many argue that the potential benefits of mastering fusion technology far outweigh the investment. Fusion promises a virtually limitless source of energy with minimal carbon emissions and without the long-lived radioactive waste associated with fission-based nuclear power. Progress and future plans. The ITER project had reached several significant milestones. Construction of many of the primary facilities is either complete or well underway, and the assembly phase of the tokamak has begun. However, when operational, ITER won't generate electricity directly. Instead, it will produce 500 MW of fusion power for 20-minute durations, a significant increase from previous experimental reactors. This will serve as proof of concept and open the door to demo, the next step fusion power plant that will demonstrate electricity production from fusion on a commercial scale. There are, however, criticisms of ITER. One of the criticisms of the ITER project is its high and rising electricity consumption. The ITER project will require hundreds of megawatts of electricity from the regional electric grid to operate its auxiliary systems, such as cryostats, vacuum pumps, heating systems, and magnet power supplies. The ITER website states that the project will produce 500 megawatts of fusion power with an input power of 50 megawatts. However, this statement is problematic, as it implies that both numbers refer to electric power. In actual fact, the output power refers to fusion power, embodied in neutrons and alphas, which cannot be converted to electricity in ITER. The input power refers to the heating power injected into the plasma to help sustain its temperature and current, and it is only a small fraction of the overall electric input power to the reactor, which varies between 300 and 400 megawatts. Moreover, this electric input power does not include the energy invested in the construction and maintenance of the reactor facility, which is also enormous. Critics point out that the ITER project will consume more energy than it produces, and that it will divert resources from more feasible and cost-effective energy research projects. Another criticism of the ITER project is its dependence on tritium fuel, which is scarce, radioactive, and difficult to handle. Tritium is a hydrogen isotope that does not exist naturally on Earth, but has to be produced artificially by bombarding lithium with neutrons. The ITER project plans to use a 50-50 mixture of deuterium and tritium as fuel for fusion, as it has the highest reactivity among possible fusion fuels. However, we run into several problems using tritium as fuel. First, there is no natural supply of tritium on Earth, and the current global inventory is only about 25 kilograms, which increases by only about 1/2 kilogram per year. The ITER project will require at least 1 kilogram of tritium annually, which will have to be purchased from fission reactors or produced in test modules inside the reactor. Second, tritium is somewhat radioactive, with a half-life of only 12.3 years. This poses safety concerns for its storage, transport, and use in the reactor. Third, tritium is difficult to handle and recover in a fusion reactor. Analyses of DT operation in ITER indicate that only 2% of the injected tritium will be burned in fusion reactions, while 98% will exit the plasma unscathed or be trapped in various reactor components. Some tritium will inevitably leak into the environment or decay into helium-3. Critics doubt that tritium can ever be supplied or managed adequately for a large-scale fusion reactor. A third criticism of the ITER project is its production of large amounts of neutron radiation and radioactive waste. The fusion of deuterium and tritium produces helium and a neutron, which carries most of the energy released by the reaction. However, these neutrons are not benign solar-like radiation, but rather high-energy particles that can damage materials and induce radioactivity. The neutrons will escape the magnetic field that confines the plasma and hit a blanket of material surrounding the plasma. The blanket will absorb the neutron energy and transfer it to a coolant system that can be used for electricity generation or other purposes. The blanket will also breed more tritium from lithium for future use. However, these functions come at a cost. The neutron bombardment will cause swelling, embrittlement, and fatigue in exposed materials, create dangerous radioactivity in all exposed reactor components, and generate huge volumes of radioactive waste that will have to be stored and disposed of safely. The ITER project estimates that it will produce 30,000 tons of radioactive waste over its lifetime, including decommissioning, of which 6,000 tons will still be dangerously radioactive after 100 years. Critics contend that fusion reactors are not as environmentally friendly or safe as they claim to be. A fourth criticism of the ITER project is its demand for cooling water resources. Fusion reactors require torrential water flows to remove heat from various reactor systems, such as reactor vessels, plasma heating systems, tokamak electrical systems, cryogenic refrigerators, and magnet power supplies. The ITER project will use cooling water from the Canal de Provence, which is formed by channeling the Durance River. The cooling water will be recirculated and discharged into the atmosphere by cooling towers. The ITER project estimates that the total heat load could be as high as 1,000 megawatts, and that the combined flow rate of all the cooling water will be as large as 12 cubic meters per second, or more than 1/3 of the flow rate of the canal. Critics point out that fusion reactors are much greater consumers of water than any other type of power generator, because of the huge parasitic power drains that turn into additional heat that needs to be dissipated on site. They also question the availability and sustainability of cooling water resources in a world where fresh water and even cold ocean water are becoming increasingly scarce. Where does that leave us with nuclear energy? Thankfully, other technologies are coming up. One of them is the stellarator. The stellarator is a type of nuclear fusion reactor that uses magnetic fields to confine a plasma, the hot and charged state of matter that fuels the fusion reactions. Unlike the more common tokamak design, which relies on a large electric current flowing in the plasma to create part of the magnetic field, the stellarator generates the entire magnetic field with external coils. How is the stellarator different from the ITER? There are several ways. Magnetic field. In a tokamak, the magnetic field that twists and shapes the plasma is formed by a combination of an external toroidal field and an internal poloidal field. The poloidal field is generated by a large electric current flowing in the plasma, which is induced by a transformer. In a stellarator, the magnetic field is produced entirely by external non-axis symmetric coils, which have a complex and twisted shape. Plasma current. In a tokamak, the plasma current is essential for creating part of the magnetic field and maintaining the plasma equilibrium. However, it also causes several problems, such as resistive heating, magnetohydrodynamic or MHD, instabilities, disruptions, and runaway electrons. In a stellarator, the plasma current is negligible or zero, which avoids these issues but also reduces the plasma stability and performance. Magnetic shear. In a tokamak, the magnetic shear is usually positive throughout the plasma, which means that the rotational transform, the angle of twist of the magnetic field lines, increases with the radius. This helps to stabilize some MHD modes and reduce plasma turbulence. In a stellarator, the magnetic shear is typically negative or zero, which means that the rotational transform decreases or stays constant with the radius. This can lead to more MHD activity and transport losses. Plasma shape. In a tokamak, the plasma cross-section is usually circular or elliptical, with some degree of triangularity or squareness. This affects the plasma confinement and stability. In a stellarator, the plasma cross-section can have various shapes, depending on the coil configuration. Some stellarators have a bean-shaped or crescent-shaped cross-section, which can improve the plasma quality. These differences give the stellarator several advantages for a fusion power plant, such as 1. Steady-state operation. The stellarator can run continuously without interruptions, since it does not need to periodically ramp up and down the plasma current. This reduces the stress on the reactor components and increases the power output. 2. Low recirculating power. The stellarator does not need to use a transformer to induce the plasma current, which consumes a significant fraction of the electricity generated by a tokamak. This improves the efficiency and economics of the fusion plant. 3. Benign heat loads. The stellarator can handle high plasma densities and pressures without producing large edge instabilities that can damage the plasma-facing components. This allows for better plasma performance and longer component lifetimes. And 4. No runaway electrons. The stellarator avoids the formation of runaway electron beams that can occur in tokamaks during disruptions. These beams can cause severe damage to the reactor walls and pose a safety hazard. The Wendelstein 7X or W7X is the world's largest and most advanced stellarator, built in Germany by the Max Planck Institute for Plasma Physics (IPP). It is designed to test the feasibility of the stellarator concept for a power plant by achieving high plasma temperatures, densities, and confinement times. It is also testing an optimized magnetic field configuration that minimizes the heat and particle losses from the plasma. Some of the achievements and challenges of W7X are high plasma performance. W7X has demonstrated plasma temperatures of over 100 million degrees Celsius, comparable to those in a tokamak of the same size. It has also achieved a record value of the triple product, a measure of the plasma quality for fusion, by using ice pellets to fuel the plasma. Long plasma duration. W7X has produced plasma discharges lasting up to 30 seconds, showing the potential for continuous operation. It aims to extend this duration to 30 minutes after installing water-cooled diverter plates that can handle higher heat fluxes from the plasma. Low neoclassical transport. W7X has confirmed that its complex and twisted magnetic field reduces the neoclassical transport, a type of heat loss caused by collisions and drifts of plasma particles. This validates the computer-aided design of the stellarator and improves the plasma confinement. High plasma turbulence. W7X has also observed that its magnetic field does not suppress the plasma turbulence, another source of heat loss caused by fluctuations and instabilities in the plasma. This limits the maximum achievable ion temperature and requires additional heating methods to overcome it. There are exciting startups that are working hard to make stellarators a reality. One of them is Type 1 Energy. Type 1 Energy has recently secured $29 million in funding from several investors, including Breakthrough Energy Ventures, which is backed by Bill Gates and other billionaires. The company plans to use the money to develop its Fusion Direct program, which leverages recent advances in stellarator fusion performance, plasma science, and high-temperature superconducting magnet technology. These technologies enable Type 1 Energy to create a low-risk short-term path to fusion energy without building another costly, large-scale science validation machine. Type 1 Energy has a strong technical team that includes experts from the University of Wisconsin-Madison, the Max Planck Institute for Plasma Physics, and the Massachusetts Institute of Technology. The company also has global partnerships with top research institutions, universities, and industrial companies in fusion science and technology. The company's CEO is Christopher Mowry, who is a former CEO of General Fusion and a senior advisor on fusion at Breakthrough Energy Ventures. Type 1 Energy's goal is to build a risk reduction platform for the stellarator over the next few years. This platform will be low cost but have a high level of performance. It will be used to test several engineering design choices made by the company and confirm the accuracy of its stellarator plasma physics models and simulations. The company hopes to develop a viable fusion power plant, FPP, that can generate electricity from fusion energy on the grid in the coming decade. Marvel Fusion is a German startup that is working on a laser-based nuclear fusion reactor, which aims to offer clean and safe energy for the future. Marvel Fusion's approach is different from the conventional methods of achieving fusion, which use either powerful magnets or intense lasers to heat and compress a plasma of hydrogen isotopes. Instead, Marvel Fusion uses ultra-short pulse lasers, which can amplify the laser beam to extremely high intensities in very short durations. These lasers are then focused on a fuel target made of boron, which is abundant and cheap on Earth. When the laser hits the boron target, it creates a Coulomb explosion, which means that the positively charged nuclei repel each other violently. This generates a shock wave that compresses and heats the fuel to fusion conditions, producing helium and energetic alpha particles. The alpha particles can then be converted into electricity using direct energy conversion techniques. Marvel Fusion claims that its technology has several advantages over other fusion methods, such as lower temperatures, higher efficiency, smaller size, and lower cost. The startup also says that its fusion reactor will produce minimal nuclear waste, which will decay within 100 years and can be recycled or reused. So far, Marvel Fusion has raised a Euro 35M Series A round from investors such as Early Bird Venture Capital and Tavet Henricus, the co-founder of TransferWise. The startup plans to use the funds to demonstrate that its laser technology works and to build its own fusion facility 5. Marvel Fusion hopes to achieve a positive energy balance, meaning that it produces more energy than it consumes by 2025.